Hey guys, welcome back. Let's go over a few of the most missed problems from the test that you guys took the other day. So this is very similar to number 2 on the test. So on this one, we want to know what's the reduced ratio in the perimeter of the area, or the perimeter from figure A to figure B. So the first thing I'm going to do is pick two corresponding sides, like let's do 5 and 7. Well, 5 and 7 is already reduced, so our ratio in this case would be a ratio of 5 to 7. And then our scale factor would be 7 divided by 5. So you might want to know, you might wonder, is it going to be 7 over 5 or is it going to be 5 over 7 for the scale factor? So I don't know, which one is the value of k? Well, if we're going from 5 to 7, one question you might ask yourself is it getting bigger or is it getting smaller? Well, if it's getting bigger, it's got to be a improper fraction, and if it's getting smaller, a reduction, then it would be an improper fraction. So when k is equal to 1, then it doesn't change at all, but if the scale factor is greater than 1, then it's going to be an enlargement. Okay, it's getting bigger. If k is less than 1, then it's going to be a reduction. It's going to be getting smaller. All right, are they similar by what postulate? So on this one we have three sides here, and the three sides here, we want to set up our extended proportion. So I want to go ahead and do an extended proportion real quick. I'm going to set up the smaller side on the smaller triangle. So the small side is 2, medium is 3, largest is 4. Smallest over here is going to be 4, 6, and 7. And then I'm going to cross multiply and check them. So when I do this one here, I get 12 is equal to 12. So far, at least the smaller sides are growing at the same rate. But when I cross multiply the other ones, I get 21 is equal to, was that going to be 24? Uh-oh, that is not true. Okay, so you can't just check one of them to see if it works. You have to check both of them. So I think that was the problem that messed most people up on number 16. They either checked the wrong one or they didn't check both of them. So be careful on that one. Number 7, are they similar? If so, by what postulate? Well, you might notice here we have this angle in between these two sides is going to be the exact same angle. So all we have to do is check to make sure these sides are the same proportion. So set up your proportion here. I got 6 goes to 3 just as 8 goes to 4. If you cross multiply, you're going to get the same thing. 24 is equal to 24. So sure enough, they are proportional. So they are similar, we would say, by side included angle side, where the angle is included in between the two sides. All right, so there were other problems that you guys missed. Make sure you watch the practice test solutions videos again. I think a lot of you guys maybe skipped the practice test or you didn't upload your answers, because I didn't have very many people that actually upload their answers. So it's also make sure you got your homework done. So I don't know, lots of things, but you got a week to get it all figured out before we do our retakes next week. Okay, so let's get into our new stuff here. So factors of 12, what does it mean to be a factor? Well, remember these multiplication cubes? Well, if I gave you 12 multiplication cubes, just imagine, put them on your desk, how many ways can you make rectangles out of them? Well, the trivial one is always going to be 1 times the number, which is basically what times something else is equal to 12. So the first one is 1 times 12. Yeah, that works. That was always my favorite one, just put them all in order because I was being lazy. And then we could take these down here and then these here. We could do, what, 2 times 6? Yeah, that would work. We could also do 3 times 4 or 4 times 3, right? So here's all the different ways you could do it. You got 1 times 12 or 12 times 1. You've got 3 times 4 or 4 times 3. 2 times 6 or 6 times 2, right? So those are all the possible factors. Kind of fun. So then you kind of get into a prime versus composite. So if prime numbers have exactly 2 factors, which are 1 and itself, composite numbers have more than 2 factors. So pretty much anything else would be composite. Or is it? So by this definition, what is a prime number? Well, the only way you can get it is 1. The only factors of 1 is 1 times 1 is equal to 1, right? So it only has 1 factor, which is 1. Well, it doesn't have exactly 2 factors, so 1 is not prime. But is it composite? Does it have more than 2 factors? No. So we call 1 just simply not prime. What about 0? Well, anything times 0 is equal to 0, right? And it's called the zero property multiplication, right? So technically, 0 has infinitely many factors because anything can be multiplied by 0 to get to 0. But if you remember, infinity times 0 is equal to 360 degrees because of previous thing. No, that's not true. All right, can you list the first 15 prime numbers? Okay, so 2 is interesting because it's the only even prime number, then 3, then 5. You're thinking it's all the odd numbers, right? But 9 is not a prime number because 3 times 3 is 9, right? Okay, 11, what comes after 11? 13. I'm going to quiz myself, see how far I can go. Not 15, 17 is prime. 19 is prime. 21 is not prime. 23 is prime. Yes, got it. 25, no. 27, no. 29, yes. 31, yes. 33, no. 35. See, notice how I'm only checking the odd numbers? 35, no. 37, I feel like it's a no, but it's a yes. Yeah, 37 is. You get it. Okay. Well, I guess we'll keep going at this point, right? 39, no. 41, yes. 43, yes. We're almost there. 46, no. Oh, that's not even number. It's late. 45, no. 47, that's gotta be it. Yeah, it's gonna be 47. And then that's the last one. 49 is not prime. Okay, cool. I did it. But man, there's got to be a better way to do it. There is. It's called the sieve of Eratosthenes. But unfortunately, it's an activity better done in class, and we don't really have class time for this assignment. So unfortunately, I'll have to wait till the end of the year to show you the sieve of Eratosthenes. I know you'll just be dying having. I got to know, Mr. Murphy. I got to know. All right, fundamental theorem of arithmetic. It's the fundamental theorem of arithmetic. It has to be important, right? It's the foundation of all of math. All right, any whole number can be written as a unique product of primes. I actually love this. Like, this is really number theory more than algebra, but man, number theory is fun. All right, so 42, basically it's like a DNA code. Every human being has a unique strand of DNA, right? And it's like your retina or your thumbprint. It's unique, right? It's really, really cool. No one else has the same one. So 42 has this unique code, which is a unique product of primes in non-descending order, which just means ascending order. And what is that number? So we can break it down to its products. So 42 can be written as 6 times 7, and then 6 can be broken down as 2 times 3. Now, at this point, we have all primes, right? We don't have any more factors of 2, 3, and 7. So it can be written as 2 times 3 times 7, and both of those, or all three of those, are to the first power. So the unique code for 42 is 2, 3, and 7. 2 times 3 times 7. What about 60? Well, 60 is 6 times 10. 10 is 2 times 5, and that would be 2 times 3. So we have 2 2s, a 3, and a 5. So we can actually do 2 squared times 3 times 5, and that's a unique code for 60. So what's really cool about having these codes, the fundamental theorem of arithmetic, is it really helps us with greatest common factor, least common multiple between the two. So for instance, the greatest common factor that we have between the two, so what's the smallest number of 2's that they have in common? That would be 2 and just 2 and then a 3. So the greatest common factor that they have is 1 2 and 1 3, which would be 6. And it's true, that's the greatest common factor. Like if it was a fraction of 42 over 60, the most we could take out would be the greatest common factor of 2 times 3, which is 6. But the least common multiple is like if we have to have a common denominator, and then that would be the greatest number that we have. So we have to have 2 2's, a 3, a 5, and a 7. So whatever that multiplies to be, that would be the least common multiple. And once you see it that way, greatest common factor and least common multiple make a whole lot of sense. And I actually didn't see that because no one showed me this until I got to college. And that's why I'm showing you. You're welcome. All right, so multiplication and exponents, really basic stuff. So if I have 2 plus 2 plus 2, isn't that really 2 3 times, which is 6? Yes. So multiplication is just repeated addition over and over again. Feels like we're like back in, I don't know, middle school, because we kind of are. It's good stuff. Multiplication. No, this is totally 4th grade. All right, so 3 plus 3 plus 3 plus 3, 12. Okay, but it's 3 4 times, which 3 4 times is 12. All right, how many 2's am I adding together? Well, 4 2's and then 1 3. So I would do 2 times 4 plus the 3, but I can't combine the 2 and the 3 until after I multiply it first, right? So what about with exponents? So if we're doing repeated multiplication, that's where exponents come from. So repeated addition is multiplication. Repeated multiplication is exponents. So it's kind of like a hierarchy. We go from addition, multiplication, exponents. Whoa, mind blown. All right, so x 3 times, right, is going to be x times x times x, which is x cubed. And that's where the exponents come in. So if we do x plus x plus x, that would be 3x. But x times x times x times x is like to a whole nother level, is x cubed. So here we have two x's, so this would be 7, there's only one 7 by the way, so 7x squared y squared, right? Because there's two x's and two y's. You could list it out as x times x times x, but you can combine them together just to make it a little bit simpler. Just like you can combine addition, if it's the same term, with multiplication. So here we have 3 2's, 2 3's, all being multiplied, by the way. So 2 cubed times 3 squared times 5 to the first power. Really cool. All right, so what is a radical? A radical is just an exponent, but it's not an integer in this case. It's going to be a fraction, or you can write them as decimals if you want to. So instead of squaring something, the square root is like the 1/2 power, right? So if we know that x squared is equal to 9, that means x times itself is equal to 9, right? Because it was x 2 times, like with multiplication being the operation. So what times itself is equal to 9? Well, you can probably think, oh, well, that's obviously 3, right? 3 times 3 is 9. Anyone can get those square roots, the perfect squares, right? Then go on the other side. X squared is 16, x times x is 16, so 4 times 4, right, is 16, so it's 4. But what about the square root of 12? Well, it's going to be somewhere between 9 and 16 because it's the square root of 12, right? So our answer's got to be somewhere between 3 and 4, right? Well, to find exactly what this is, you actually have to put it in the calculator. So let me pull up my calculator real quick. Oh, isn't that nice? Anyway, so what we end up doing is we take the square root of both sides, and we're going to take the square root of 12, and lots of different ways you can put it in the calculator. Let me show you a few. So I'm going to do 12 and the caret button, which is my favorite way to do it, 1/2 power. I'll give it to you as a decimal, or you can hit second x squared, which will give you a little radical, 12, and give you the exact same thing. All right, so that is approximately 3.46, which is between 3 and 4, just like we would expect it to be. So the buttons you might push would be second x squared, which will give you the little radical symbol over the top, 12, or you can do 12 caret to the 1/2 power of 0.5. If you're putting it in on your phone, you might have to put 12 in first and then hit the radical button, and it'll give you the 3.46 if you're doing it on Android or iPhone. Alright, so let's reduce some radicals. I think I already gave you an example of radicals are like high school, and I might keep with that one, but I really got to do the shoe store, which is more like middle school, but hey, whatever. Alright, so if I have the square root of 450, I want to break it down to its unique product of primes, and then any even pair of primes I can take out. So that would be 10 times 45. 45 is 5 times 9. 9 is 3 times 3. 10 is 2 times 5. If you notice, the red ones are where I'm stopping because those are prime numbers and they can't be broken down anymore. So just keep breaking it down until you find, can't help myself. I need to go to bed. Anyway, until you can find all the products of the primes. Alright, so this, once we have that in the square root, we're looking for any pairs to be able to come out, any perfect squares. So in this case, it looks like we have 2 3's and 2 5's that can come out of the radical. So radicals are a lot like high school. So everyone's all kind of sorted off, and then everyone pairs off, and they wander, they graduate and get married and have a bunch of cute kids and post it on Facebook and stuff like that. But the lucky few, the proud, the Marines, no. The Mr. Murphys are left all by themselves, still stuck in high school for the rest of their life. Depressing moment, but there's a smirk on my face because it's hilarious. Self-owned. Okay, so everyone else paired off. We had 1 pair of 3's, 1 pair of 5's, and then the 2 is all by itself, left still inside the radical because it wasn't able to be reduced. So what's happening here is we're taking the square root of 3 to the second power, but the square root is really the 1/2 power, and this is also times the 1/2 power. So we end up with 2 to the 1/2 power if we distribute the square root through to all the terms. So we end up 2 to the 1/2 power times, well, half of 2 is just 1, so that's 3 to the 1, times 5 to the 1, which ends up being 3 times 5 square root of 2. And that's it. And then when we're done, we're going to multiply that back together, which is 15 radical 2. All right, so shoe store example. You go into a shoe store and it's a mess. Nothing's sorted, nothing's in the box like it's supposed to. So you sort it out and you find you have 1 2, 2 5's, and 2 size 3 shoes or whatever. So anything that's a matching pair, you can take it out. So we take the 2 Converse and we take them out, and one shoebox. Now one shoebox is kind of like saying, well, now it's just one of them instead of having two of them or whatever. So this is our, in this example, this is our 2. And then over here we have 2 5s. We put them in a shoebox, we take them outside of the store. And this was, in this example, this was our 3. Whoa, that was weird. 3. Okay. And then what was left over was our 2. I'm sorry, this is actually our 5. And then we take our 5 and our 3 when we're done, and then we throw it into our closet. We take it out of the box, throw it in the closet, and they're all mixed back up together because we're going to multiply it back when they're done. All right, so that's 15 radical 2. And what's left in the shoe store, that 1 2 all by its lonesome self. Don't worry, you won't be lonely forever. Or maybe you will. Lies. All right, so break this down. Break it down. That's going to be 9 and 3 and 3. And then it looks like I got a matching pair of 3s, which can come outside. Oh, look, we already had a 5 on the outside. So those are like the shoes that you already have in your closet. So I know you say, but Mom, I literally have nothing to wear. I never say that, you know, but it's a thing I've heard. We all know you actually do have shoes, and I could show you the shoes in my closet, but I won't because it's a lot. Anyway, so we have 3, which comes out to join the 5 that we already have. So again, that's like times 1/2, and then that basically goes on the outside, right? And now it's able to come out. So we have 3 times 5, which is going to be 15, radical 2, all left on the inside by itself. It's okay. All right, so the 5 is like the shoes you already had at home. The matching 3s are the ones that you were able to take out, and the 2 was the one that was all by itself. So we were able to take the 3 and the 5 and put them in here, and then we took it out, and then, whoa, anyway, and then we took it home, and then we immediately took it out of the box, threw away the box, and, or recycle the box, whatever you want to do, and then those are the ones at home. So 3 times 5 is 15 times 2, I know, so cool. All right, 120, that's going to be 12, 10, 5, 2, 6, 3, just kidding. There's lots of different ways to do that, by the way, 2 and 2. All right, any matching pairs? I got matching pair of 2s, and that's it. So the 2s come out, everything else has to stay in. So I have 1 2, 1 5, and 1 3. Now when I'm done here, just like I combined everything back together with the 3 and the 5, same thing's going to happen. The 2 times the 3 times the 5 is going to be all combined back together. Just multiply it, and when we do that, we'll get 30. So this radical 120 will reduce down to 2 radical 30. All right, let's do one more. That's going to be 10. That's 2 and 2, 2 and 5. All right, so I've got 3 of these, but I can only take one matching pair. So that's going to join the 3 that's already out there. And when I do that, these are going to be multiplied back together, which is going to give me 6 radical 10. And the 2 and the 5 that were on the inside, they get multiplied back together as well. All right, let's do another one. It's fun. Oh, I think this is 27. It can be a little tough. If you see a number, just try your prime numbers. Try 2, try 3, try 5, try 7, and then try 2 again, and 3 again, and stuff like that. And eventually you'll get all of them. If you find a bigger one, you can split them up earlier, and it'll save you some time. All right, so 12 is going to be 3 times 4. 4 is 2 times 2. That's going to be 3 times 9. 9 is 3 times 3. All right, any matching pairs? I got some 3s here, got some 2s, and I got some 3s. Oh, cool. Everything in this one's coming out. And that's because all of these, we had 2 2s and 4 3s, right? Because all of these are an even power, right? So when I take out half of those, that's going to be 2 on the outside. And when I multiply that by 1/2, that's going to be squared, right? So it's going to be 2 times 3 squared. Radical, I don't know, x to the 0th power, which is just 1, radical 1. So basically, when everything in the shoe store is matching pairs, we end up with a radical 1 at the end. And if there's no more shoes left in the shoe store, it closes down. They can't do any business, so they just go home. All right, combining like terms, the next part we're doing here. Some variables, like terms, are the same variables to the same power. So for instance, 3x squared minus 2y squared plus 2x squared. Well, x squared and x squared are like terms because they have the same variable to the exact same power. Now, x squared and y squared are not like terms because they're different bases, right? Different variables. So if they're like terms, we can add them together. So 3x squared plus this 2x squared is going to give me 5x squared minus the 2y squared. And I can't add those together because they're not like bases. Same thing here, x plus 3x is going to be 4x, right? They're both x's and they're both understood to be to the first power. So we can go ahead and combine them together, add and subtract them, right? The x squared, the 2 and the 3, well, the 2 and the 3 are both constants, right? technically you can think of a constant as like anything to the 0th power, because anything to the 0th power becomes 1, and so, well, whatever. So it's got the same power of 0 and the same variable of x, and so those are constants basically. And so we can add them together, and that will give us this thing. All right, 2x squared plus 5. All right, same variable, same power. I see x squared. So easy when I color code it, right? That. So 4x squared minus 3x squared is just going to be x squared. 4y squared minus y squared is going to be 3y squared. So x squared minus or plus 3y squared. Now, the exact same thing we do with looking for like terms. Check to see if they have the same variable and to the same power. We do the same thing with radicals, because radicals are really just the half power. So it's the same thing, but instead of being to the 2nd power, it's now being to the half power. So the x to the 1/2 and the x to the 1/2 are the same, and so we can do the same thing as we did before, just with different powers. And instead of being the 1/2 power, that's the exact same thing as a radical. So a radical is the 1/2 power. So it's the exact same thing if you notice that. So the patterns follow exactly the same. So when can we add radicals? We can only add radicals when they're the same power of a radical, like a square root or a cube root or 4th root or something like that, which all of ours will be square roots for this year. And if they're the exact same variable, which is meaning it's the same part in the radical itself. Otherwise, they're like different variables, like square root of x and the square root of y, 2 different things. Square root of 2, square root of 3, 2 different things. So, properties of radicals. Same base to the same power, we can add them together. That's going to be 4x, right? 4x to the 1st power, technically. All right, square root 2 and 3 square root 2 would be 4 square root 2, right? So if you have 1 square root 2 plus 3 more square root 2s is equal to 4 square root 2s. I'm feeling very elementary today. Same thing, but these are different variables, right? So we can't add them together, so we're done. And same thing with radical 2 and radical 3. They're 2 different things. We have 3 radical 2s minus 2 radical 3s. They're not the same thing, so we can't go ahead and subtract them. So that's already simplified. So x plus y plus x would be 2x to the 1st plus y. I can add the radical 3. I have a radical 3, a radical 2, and another rad 3. So that's going to be 2 radical 3 plus rad 2, vice versa. I guess you can prioritize it from least to greatest order, so the radical 2 can go before the radical 3. On this one, I've got the same power here, so I can go ahead and add them. I got the same power, same terms on that one as well, so that's going to be x plus 3y. And the same thing with the radicals. I've got radical 6. I can go ahead and do that, add them together, add those together as well, because they're the same power to the same base as well. All right, let's do the assignment. Whew. If it feels like we went over 2 days worth of stuff in 1 day, it's because we did. But it's easy. Let's do number 1. Break it down. All right, 2 times 9 and 3 times 3. Do you see any like terms? I see 2 3s. So the 3's can come outside of the radical, and then what's left on the inside of the radical is going to be the 2 all by itself, all by its lonesome. And check your answer bank, and you should have it. Break down 2. So this is an even number. I can cut it in half, which will give me 36. And 36 you might recognize as a perfect square of 6 and 6. Now we could keep breaking these down as 2 and 3 and 2 and 3. Then we take out 2 pairs of 2's and 2 pairs of 3's. But what's nice about this is if we notice a matching pair, like a perfect square here, we can go ahead and take it out. Uh-oh, I already had a 5 on the outside, so what do? Well, it's going to be, well, that was weird. Let's try that again. All right, so it's going to be 5 times 6 radical. What's left on the inside? Just the 2 all by its lonesome. And then go ahead and multiply those together, which will give us 30 radical 2. 13. All right, so this is seeing if we can actually combine like terms. So we want to see if we can add them. Well, they're both radical 6's, right? So I have negative 5 radical 6's plus 2 more, which is going to leave me with negative 3 radical 6. So negative 3 radical 6. Think of the negatives as debt. So if you owe 5 and you get paid 2, you pay off your debt, you still owe 3, right? All right, 15. They are like terms, right? Rad 10 and rad 10, so I can add them together. So together, that's going to give me 4 plus 5 rad 10s is going to give me altogether 9 radical 10. I've got some like terms here and here, rad 3's and rad 3's. So negative 2 rad 3 plus 3 rad 3's is going to give me 1 rad 3 plus 2 radical 6. So that's going to be radical 3 plus 2 radical 6. Now, the rad 6 and the rad 3 are not like terms, so I can't add them together. I didn't mean to get rid of all that. I don't know what's happening. Being sidetracked. Okay, 23. So on this one, ooh, rad 8 and rad 2, can't do it, I'm done. But you need to check on these because sometimes they'll actually reduce. So that's going to be 2 and 4 is 2 and 2. The 2's can come out, joining this one out there. So that's going to be 6 radical 2, right? Okay, so now that we have 6 rad 2 minus 2 rad 2, that's going to be equal to 4 radical 2. And that should be your answer. All right, we're going to have to reduce this one as well. So that's going to be 3 and 4. 4 is 2 and 2. We got my perfect square. Pull that one out. So that's going to be minus 4 radical 3. Okay, so 2 radical 3 minus 4 radical 3 is going to give me negative 2 radical 3. In case you're wondering, you did do radicals at the beginning of Algebra 1 last year. So everybody should have this stuff. All right, break it down. That's going to be 2 and 9. 9 is 3 and 3. I see my matching pair. So that's negative 3 radical 2. That's going to be 4 and 3. 4 is a perfect square. Pull the 2's out to join the 3, which is going to be 6 radical 3. Ooh, those are not the same. Oh man, my brain hurts, but I can do it. All right, 3 and 9. 3 and 3. So the 3 comes out. So it's going to be minus 3 radical 3. Okay, these are like terms, rad 3, rad 3. So combine those, but this one stays by itself because there's nothing to do with it. So negative 3 radical 2 and 6 rad 3 minus 3 rad 3 is going to be equal to positive 3 radical 3. So plus 3 radical 3. And those are not like terms, tomatoes, tomato, and I am done. And that was all under 30 minutes. I went over 2 days worth of lessons in less than 30 minutes. I'm done. If you have any questions, please do make sure you ask. Radicals are going to be really important whenever we get to Pythagorean theorem and its converse and special right triangles. So make sure you got radicals down. Usually it's one of them I like to do in class because we get to do other fun stuff too, like civ Aristosthenes. But Mother Nature had different plans for us. So we will move on with radicals so that we can do our game that we were going to do in class whenever we come back, and we'll see if we're back in school by Thursday. I'm not sure, but you wouldn't be watching this video if you were a B student anyway. So I'll see you guys later. Have a good one. Bye bye.